on to space-time diagrams, part 2. What we want to do here is explore the concept of velocity as it's represented on a space-time diagram. Let's just remind ourselves here what a space-time diagram is. We actually have 4 cases this time. So we're going to imagine that we have our spaceship or car traveling along the x-axis. And it's going to give off flashes at certain points in time. And of course, we have our grid or lattice of clocks all along the x-axis at any given point, so that when that flash occurs, a photograph will be taken and it will record the location of that clock where the photograph occurred and the time on that clock. And all the clocks along the x-axis we will assume are synchronized using a method that we reviewed in a previous video clip. So, got our spaceship. We're going to imagine 4 trips now, 4 passes or 4 runs of our spaceship along the x-axis. And all of them will start at t equals 0 and x equals 0. So they'll all be starting at the origin here. We don't have to do that, of course. We did an example where we started at someplace different than the origin, but for our purposes here, we'll just always start at the origin, t equals 0, x equals 0. And then we've got run 1, run 2, run 3, and run 4. So let's just review what's going on there. So run 1 starts at x equals 0, then at t equals 1, it's at x equals 1, t equals 2, x equals 2, and so on and so forth. And that is this space-time diagram here, or this, I should say, this world line right here. Remember, the world line represents the path of an object through space and time. And so at t equals 1, it's at position 1, x equals 1. At t equals 2, it's at position 2. At t equals 3, it's at position 3, and so on and so forth. So this is the world line for run number 1 of our spaceship as it's traveling along the x-axis. You'll probably get sick of me saying this, remind you of this, but this is not, the spaceship is not going up at some angle. The spaceship is constrained to move only in one direction along the x-axis. We'll assume it's moving in the positive direction. It could move the other direction as well. But only one direction, back and forth along the x-axis. All our examples here, it's moving just to the right in the positive direction. So that's run number 1. Then we reset things and come back, and it starts another run. At t equals 0, it's at x equals 0, and then 2, 4, 6, 8. So it's at t equals 1, it's at 2. At t equals 2, it's at 4. At t equals 3, it's at 6. And at t equals 4, it's at 8. So that is run number 2. And this is the world line of our spaceship in run number 2. Run number 3 goes at t equals 0, again, starting at x equals 0. Then t equals 1, 1/2, and then 1, 1/2, and 2. So at t equals 1, it's at 1/2 here. At t equals 2, it's at 1. T equals 3, it's at 1.5. T equals 4, it's at 2. And we will assume that we have clocks, in between here at every single point that we need. And then the 4th run, just to do something different, we'll assume it's actually moving in the other direction now. So it starts at 0 again, but then goes at time t equals 1, it's at -1, and then -2, -3, 4. So at time t equals 1, it's at -1. Time t equals 2, it's at -2. Time t equals 3, it's -3. And then at time t equals 4, it's at -4. Okay, so 4 different runs of our spaceship. Now, let's remind ourselves about the concept of velocity. We probably all sort of know it, depending on how much you've done things like this. You may not have thought too much about it, but we know that velocity is distance divided by time. Distance covered divided by, say, elapsed time. Okay, distance divided by time, right? Miles per hour, kilometers per hour, feet per second, meters per second, and so on and so forth with that. So how does that relate then to our diagrams here, or our world lines here? Let's take the first one, number 1 here. Run number 1. Just looking at it, we can say, well, we went we'll just say we're using meters here. So we went 1 meter in 1 second, and then we went 2 meters in 2 seconds, and then 3 meters in 3 seconds, and 4 meters in 4 seconds. Pretty clear we're going 1 meter per second. But if we want to calculate that, we could say, let's just take the 3 here. X equals 3 in 3 seconds. 3 divided by 3 is 1 meter per second. Or 2 divided by 2 is 1 meter per second. And because it's a straight line, as we talked about before, that's a constant velocity situation. And we're going to use that in just a minute. Let's look at number 2, though, which is this one here. Note that in 1 second, we're going 2 meters. So the velocity at that point, or over this distance here, would be 2 meters in 1 second, 2 meters per second. Or we've got 4 in 2 seconds. 4 divided by 2, 2 meters per second. Or 6 in 3 seconds. 6 divided by 3, again, 2. And so on and so forth. 8 divided by 4 is 2. So velocity in this case would be 1 meter per second. Velocity in this case is 2 meters per second. Velocity in this case, again, because it's a constant velocity, we're not changing the velocity. We can just pick any given point and read it off. But we've got 1/2 meter in 1 second. So that's 1/2 meter per second. If we did 2 meters in 4 seconds, 2 distance divided by 4 seconds, 1/2 again, 1/2 meter per second. And then the final version is -1 meter in 1 second, -2 meters in 2 seconds. So we're going -1 meters per second, the negative sign indicating motion to the left. Okay, we take motion to the left as negative, motion to the right as positive. And again, this is motion just along the x-axis. These are the world line representations of that motion along the x-axis. We're applying the time as the vertical axis here. Okay, what's the big point here? Because that's pretty straightforward, maybe pretty obvious. Well, let's relate the velocity here to the slope of these lines. And again, for those of you who haven't had math recently, don't worry, we're not going to do too much with slope. You may, way back in your memory someplace it may be there, but you haven't done much with it for a long time, so we're not going to go into the details too much of it. But here's what we are going to do. We're saying, okay, velocity is distance divided by time, essentially. So let's look at, we'll do this example right here. Let's look at number 2 here. So the distance traveled, say, from here to here. That's not a very straight line. So there's the distance traveled, and here's the time. Okay, so essentially, dropping things today. Essentially what we're doing is distance traveled is 2 divided by the time 1. Again, depending on how much algebra and the like you remember, sometimes we call this the run. Okay, the run here, and we call this the rise. Sort of intuitive, the rise, how far you've risen in a given, over that given distance. So you have a distance of 2 for the run there, getting all the way over to 4, and the rise is 1. So run is a horizontal distance, rise is a vertical distance. Run on our space-time plot represents x distance, how far it's gone along the x-axis. Rise represents distance, in a sense, in time, how much time has elapsed. So we can say that on our space-time diagram, velocity equals, remember, velocity is distance divided by time. Velocity is run divided by rise. Is run divided by rise. Okay, so if I didn't have these numbers here, and I wanted to calculate the velocity of any given world line here, or really the object, which the world line represents, its motion, I just pick 2 points, and I calculate, okay, how far has it gone? Run. How long did it take? The rise, and that's the velocity for me. You might say, okay, well, that's, again, not too complicated or complex or anything. You're stating almost the obvious here. But let's look at this in terms of the slope of the lines. And for our purposes, the slope of the line is whether it's sloping sort of downward or sloping upward. Okay, so it's the angle of the line compared to the x-axis or the time axis here. So clearly we can see number 2 has a higher velocity because you're getting more run for a given amount of rise. You're covering more ground for each second that you're going here. And number 3 has the least amount because in 1 second you're only going half a meter, whereas for number 2, in 1 second you're going 2 meters there. So what we can say in general is that when the slope of a line, and the steeper the line is, the higher the slope, we say, and we'll get to the exact definition here in just a second, or the semi-exact definition. The steeper the line is, okay, we say this line has more slope. It slopes upwards more than this line. But for the space-time diagram, the line that has a lower slope, this one, represents a higher velocity than this one. And this will be a key point to remember in some of our later episodes when we talk about special theory of relativity and do a few more space-time diagrams and things like that. Okay? So the lower the slope, the smaller the slope, the less the steepness of a line really represents more velocity because you're covering more ground in a shorter amount of time. Whereas if you have a steep slope, you're covering a short amount of ground in a longer period of time, so the velocity is less. And just to remind you, the official definition, or say the first definition of slope you probably learn, is that the slope of a line equals rise over run. Okay? So it's a measure of the steepness of a line. So it's how far does it rise within a given run. So what's its y value for a given x value? If you have a large difference in y for a small difference in x, you have big difference in the rise. A big rise over a relatively short run gives you a larger number for the slope and a steeper line. Okay? But velocity, we can see here then, is inversely related on a space-time diagram to the slope. Steeper slope, like number 3 has the steepest slope here, but it represents the slowest velocity of our examples. Whereas number 2 has the lowest slope, and it represents the faster velocity. Again, it's nothing profound here, just because we're measuring the run here, how far it's traveled x in a given amount of time. So if it travels a long distance in a given amount of time, like a second, it just means it's going faster. That's all we're really saying. But again, the concept here is to recognize that steeper slope means lower velocity, smaller slope, lower slope as it were, less steep of a line, higher velocity. And then this one just means we've got a velocity going in the other direction. So these lines have positive slope because the rise and run are both positive values that run that way and the rise up. This one actually has a negative slope because it has a negative positive rise but a negative run there. And again, we're not going to get into all the niceties of that, but I want you to remember the concept of just being able to look at a picture for a space-time diagram and see a given world line, which will be, for our cases, straight lines, because we'll be doing constant velocity situations, and recognize, oh, this represents a slower velocity than this one, even though this is a steeper slope. And then one more thing here. You know, we talked about these as being 4 different runs for a spaceship. We could also represent them as 4 spaceships all taking off at the same time from our origin. And spaceship number 1 follows that path along the x-axis. Spaceship number 2 goes faster. Spaceship number 3 goes slower. And then spaceship number 4 actually goes off in the other direction. And so again, if you use sort of the animation principle that at x equals 0, that's what it looks like. They're all at 0. At x equals 1 here, if we took a snapshot of the whole x-axis, these would be the locations of our 4 ships. This is one going that way, and this is number 3, number 1, number 2. And then take another snapshot of the whole x-axis. Where are the locations of our ships at that point? The dots represent them, and then t equals 3 and t equals 4, and so on and so forth. Okay, so good to just play around with this a little bit, space-time diagrams, get a feel for what's going on, make up your own little numbers there and do some plots and things like that. And you know, just that the writing down of things, hopefully will get it to stick in your brain a little bit more. So moving on, some of the next topics we'll be covering in the video clips. A big topic is the concept of frames of reference. And then we'll move on to something called the Galilean transformation. Again, this is laying the foundations for some of the key things we'll be doing in the special theory of relativity in weeks to come.